got the other two solutions, but you can see sometimes using substitution can actually be a little bit tricky. Now let's get to Lagrange's little idea. Lagrange noticed that there's always a free optimization problem in n+1 dimensions that has the same solution as the constrained optimization problem in n-1 dimensions. He might have stumbled upon this fact by following some logic like this. First, you have to note that any constraint function can be written in the sort of normal form we've been using, g of x, y equals 0. Here we're using two dimensions, x and y, but all of this intuition is going to hold in higher dimensions. So when we think about the function this way, it's kind of on the same footing as f of xy, right? It's just a function g, which can take, whatever value it takes when you plug in arguments for x and y. It doesn't necessarily have to equal 0 when you think of it like this. Now, we can take a look at the gradient of g of xy. So let's go ahead and use the example of the unit circle from the last problem to actually draw the gradient field. And we're also going to draw the unit circle in here, which is the curve g of xy equals 0. And notice that the gradient field of g is actually perpendicular to that curve g of xy equals 0. And that's kind of a general feature of these kinds of curves. They're called level sets. And you can intuit why this is the case by thinking of g of xy like the height of a mountain. So if I choose some fixed height, I'll call it here big G, then g of xy equals big G is a contour line. It's a line of equal height, and the gradient of g points uphill. It would be too much to cover to get into this really deeply, but it turns out that the gradient field of some differentiable function, g of x1 through xn, always has this property. In other words, the fixed height solutions, again called level sets in fancy math speak, are defined by the n-1 dimensional shells that are perpendicular to the gradient field. Now, this is pretty useful because it means that the gradient field of g is precisely the directions that we cannot go when we're searching the input space if we want to keep g equal to some value, for instance 0. Now let's think about what kind of extrema we can have for f when we are optimizing along one of these contour lines of g. We really have two kinds of extrema. So we have local kind of honest to goodness extrema of f that just happen to be on the contour that g equals 0. And we also have these sort of induced extrema on f that only exist because we're not allowed to go in the direction that f is growing. In a way, we've kind of solved our problem with this observation. Because we know how to find optima of the first kind, that just happens when the gradient of f is equal to 0, and we can just check those points to see if they're on g equals 0. And for the second kind, we just said that it occurs when the direction that f is growing is precisely the direction that we can't go. That, of course, can be translated mathematically into saying that the gradient of g is in the same direction as the gradient of f. Algebraically, we can write that like this, saying that the gradient of f is equal to lambda, which is just some number, times the gradient of g. So they're some multiple of each other. Of course, that condition on the gradients isn't enough on its own. We also need to enforce that g is actually equal to 0 so that we're on the correct contour. So Lagrange came up with a really nice way to package all of this together. And what he said is, well, let's look at this function L, which is f minus lambda g. And we've added a new dimension to the problem here, lambda, which is in addition to the original xi. So a free optimization on L gives us a system of n+1 equations. The first n derivatives simply say that the gradient of f is proportional to the gradient of g. And the last equation, the one that's the derivative with respect to lambda, just gives us back the condition that g is equal to 0. So perfect. Doing a free optimization on L gives us exactly the condition that the gradients need to be pointing along the same line, and that we're going to be on the shell where g equals 0. And so the nice thing here is that this system of equations is going to have solutions that are both of the extrema that we talked about before. So for extrema of the first kind, an honest to goodness maximum minimum stationary point of f that just happens to be at g equals 0, we can see that this is going to occur when lambda is equal to 0. So when lambda is equal to 0, L is just equal to f. And when lambda is not equal to 0, that means that the gradient of f is pointing in the same direction as the gradient of g, and that final condition is going to enforce that g equals 0. Pretty cool. To wrap up, let's take a look at one of the examples that we looked at before, and this time we're going to solve it with Lagrange multipliers. So let's revisit f of xy equals minus 3x squared minus 10y squared on the unit circle. So setting up the Lagrange function and doing a free optimization will give us our solution. First, we have L of xy equals minus 3x squared minus 10y squared minus lambda times x squared plus y squared minus 1. When we take the gradient of this with respect to x, y, and lambda, we get minus 6x minus 2 lambda x for the x component, minus 20y minus 2 lambda y for the y component, and of course x squared plus y squared minus 1 for the z component. Setting all of these equal to 0 and solving for x and y gives us our solutions. Here we can see from the first equation that either x is going to be 0 or lambda is going to be minus 3. If x is 0, then we can use the constraint equation to see that y has to be plus minus 1. If lambda is minus 3, then from the second equation, we have that y has to equal 0, and plugging that back into the constraint, we see that x equals plus minus 1. And these are all 4 of our solutions. So using Lagrange multipliers, we did find all 4 solutions. When using substitution, we had this nasty little confusion with the boundaries. And there you have it. That's the Lagrange function, a function that lives in n+1 dimensions, but has the solutions to the optimization problem of an n-dimensional function, which is constrained on an n-1 dimensional shell. For some final notes, in order to keep this video short, I had to omit a couple of practical details. So here are some important things to note that I'm just going to give without proof. First, Lagrange multipliers are really easy to extend to situations where you have more than one constraint. In fact, that's one of the reasons they're so powerful. For a problem with k constraints, where you have these k equations g sub I, you simply add a new multiplier lambda I for each constraint, and then you make your Lagrange function f minus the sum of all of those lambda I times gi. This is going to give you a system of n plus k equations, and the solutions to those equations are going to be your stationary points. If you understood most of the stuff in this video, you should be able to figure out why that works. Second, because this whole scheme is based upon finding situations where the gradients align, you can run into some trouble when the gradient of g happens to be 0 on the contour where g is equal to 0. If this is the case, you're going to have to come back and manually check those points for